Well, good evening, everyone, and I want to thank you all for joining us tonight. My name is Pete Eberle, and I'm with the Northern Chapter of the Colorado Renewable Energy Society. For those of you who are new to our events, CRES and its local chapters provide education, policy advocacy, and community engagement that accelerate Colorado towards a carbon-neutral future powered by 100% renewable energy. Founded in 1996, CRES is a 501c3 not-for-profit organization that's supported by our sustaining individual and business members, as well as donations. I'd like to give special thanks to our Northern Colorado business members that include Benchmark Electrical Solutions, Sandbox Solar, Solaris Energy, Poudre Valley Rural Electric Association, and Platte River Power Authority. So without further ado, it's my pleasure to introduce our speakers for tonight, Brad Smith of Fort Collins Utilities and Mike Missimer of MGI Mechanical.
Thank you, Peter, and thank you, CRES, for having us. I'm joined with, in this presentation with Mike Missimer, so we've got a great resource with us tonight. So thanks for the opportunity to kind of come and meet with you guys and provide a little information and have a discussion on how and why air source heat pumps are well suited to our Colorado environment. One of the things I was thinking earlier today is I should almost preface this with it being a Colorado environment. It's not just an outdoor environment, but really kind of a climate-related environment, a jurisdictional environment, and a number of different things that go into that one single word there. So I'll kind of jump right into this with what really is the driver for us and the city of Fort Collins and many other communities, and it really is the basis of our work. So it's what directs our work, and it's the foundation laid within our climate commitments that really kind of inform us on where we're headed. So if you aren't familiar with the city of Fort Collins climate commitment, it is on the screen here, and what we're looking to achieve. We've already surpassed the 20% reduction of greenhouse gas emissions over our 2005 levels in the year 2020. We did meet and achieve that. Our next target is the 80% reduction in those emissions by the year 2030, and that's largely going to be the focus of this presentation tonight. And then obviously we're targeting carbon neutral by the year 2050, so some pretty ambitious goals ahead of us. So within the last couple of years, we have developed what we call our climate future, or we kind of refer to it as OCF. And this is a conglomeration of our plans and policies all rolled into one, and really our climate commitments are part of this. So within this Our Climate Future, or OCF plan, there are really three primary environmental goals that we aim to achieve by the year 2030. First, as I had mentioned before, is to reduce greenhouse gas emissions by 80% below our 2005 levels. We aim to also achieve 100% renewable electricity and zero waste and/or 100% landfill diversion, all by year 2030. So how do we go about doing this? Well, within this plan, we have established what we call 13 big moves. It's kind of the critical path. And accompanying those big moves are a series of next moves. Now, one of the 13 established big moves is number 6, efficient emissions-free buildings. So I'll dive into this a little bit and really what this looks like, this big move number 6. The next move that accompanies this is really to develop an energy performance path for new construction to zero carbon buildings. That's all laid out in our 2030 plan. What this really means is, we're looking for high-performing, highly efficient, low-load buildings. And as many of you know and can imagine, that's well suited to electrification. The plan at this point is to really develop this through building code, and starting with the adoption of 2021 body of codes, which we should be bringing to council in the next few weeks here, is an electric readiness provision. That electric readiness provision mentions or encourages heat pump installation, and if they decide to install fossil fuel burning appliances, they need to provide electric circuits within distance of those appliances for future fuel switching. We also need to look to expand our programs for electrification of space and water heating, and this largely involves our existing building stock. As you can imagine, this is the big hurdle in the room. So we'll also need to evolve those programs to space heating, cooling, and water heating with efficient heat pump technologies. So aside from these two things, there is also an accompanying 2-year tactical plan that goes along with our big moves and next moves. And this kind of provides us a biannual review and adaptation of the work that we're doing. And right now, there's an emphasis to explore and pursue efforts for building beneficial electrification. So this slide shows a graph of what our community carbon inventory emissions look like currently, or well, as of within the last couple of years. This kind of gives you an idea of what work is ahead of us right now. So you can see the red arrow down below shows our 2030 target. What you see on screen, kind of the orangish pink color, is our OCF big moves, our critical path. Gets us about halfway to where we need to be to our 2030 target. All of the accompanying moves take us that further drop down to our 2030 target. So fortunately, our power providers are prioritizing decarbonization as well. And Platte River Power Authority, or PRPA, has a 2021 integrated resource plan that has projected, that was developed with its owner communities. Those owner communities are City of Fort Collins, City of Loveland, Longmont, and Estes Park. And they projected non-carbon electricity generation capabilities of greater than 50% within their 2021 plan. So the graph on the right kind of gives you an idea of what that combination of renewables looks like, non-carbon resources. So right now, if you take wind, hydro, and solar, you end up with just over 50% non-carbon electricity generation. Now, this doesn't always mean that at any given time we're getting our electricity from non-carbon sources. So one of the cool little tools that they've developed, I've provided a link here that gives you real-time energy production, so you can see at any given time where your electricity is being generated from. In addition, since we're kind of talking broader community here, Xcel Energy also has, through their carbon reduction plan, a target of 100% carbon-free electricity by 2050. And within that plan, they lay out a scenario that says that the scenarios would limit warming to 2 degrees Celsius. Emissions from natural gas use in buildings are reduced 0 to 20% by the year 2030, and 30 to 75% by the year 2050. So provide a little bit of the good to this. What you see in the graph on the left here is net electricity generation from the state of Colorado. This is as of October 2021. It gives you kind of an idea of our electric mix right now. So between hydroelectric and non-hydroelectric renewable resources, we've increased our renewables dramatically statewide. So the bad to all of this is that in consumption, electricity is only a fraction of natural gas. And the image below shows within Western states really what percentage of, oops, I jumped ahead there, sorry. What percentage of homes are heated with natural gas and what percentage of homes are heated with other sources. So to provide a little more context, a little more local context, on average, there are about 2.4 million homes in the state of Colorado, and well over half of those homes are heated with natural gas. To become even a little more local, in the city of Fort Collins, we average about 400 new construction home permits and 25 multifamily building permits annually. In some of our surrounding communities, we're seeing about the same numbers and even more. In 2021, the city of Windsor saw over 900 single-family home permits. Nearly all of these are being heated with natural gas. Now, I don't want to be all doom and gloom, so I will say, I will leave you with this on this slide, that change is coming. We are starting to see some interest from developers and builders. In Fort Collins, we have an upcoming large multifamily development that is planning to heat and cool the entire development, all of the apartments within the development with heat pumps. Many developers are now having that conversation, of what an all-electric development would look like. One of the reasons they're doing this is they recognize that the gas infrastructure is an expense. As an average, just to give you guys kind of an idea of what it looks like, so once natural gas is brought into a development, the average price to run that gas line into each premise or each lot is about $2,400. So that adds up. If you've got a development that's building hundreds of homes, that's a significant expense. So although there's a lot of work underway, there's still a lot of work ahead of us. There's some things that we need to overcome as a jurisdiction here in Fort Collins, and one of those things that we have in front of us right now is looking at adapting our electric rate and service fee structure for homes and developments. So it's not as easy as just flipping the switch and going all electric right now. So there are a lot of things that need to be done before we can just make that happen tomorrow. So I guess one of the things I'd like to say is, it's a good time to be talking about heat pumps. So why heat pumps right now? So in this slide, I'll kind of give you a little information on really why this is a viable option. So as most of you know that live in the state of Colorado, the majority of our population lives on the Front Range within Colorado. Most of that Front Range is within Climate Zone 5. You can see that on the green on the map to the right. Most of Climate Zone 5 has an outdoor winter design dry bulb temp, HVAC design dry bulb temp when designing HVAC systems, temperature of between 0 and 10 degrees Fahrenheit. Most of the cold climate heat pump offerings that are available on the market today maintain a high efficiency at a 5-degree temperature or lower. So we're seeing viable options that can very much work within our climate zone. So on this slide, this is some information from a Fort Collins and Longmont study that was done. We hired a third-party consultant to perform an electrification study. The primary focus of that electrification study was on space and water heating. So within this study, modeling projections of hourly load shapes and monthly energy, we found that the majority of Fort Collins annual space heating loads occur primarily between 20 degrees and 40 degrees Fahrenheit. So circling back to the previous slide, I want to reiterate that most of our Climate Zone 5 winter outdoor design temps fall within that 0 to 10 degree Fahrenheit range. And again, most cold climate heat pumps maintain high efficiency at 5 degrees Fahrenheit or lower. So since we can't and probably shouldn't talk about all of this without discussing the impact electrification would have on our electric grid, I want to provide this graph. So this graph shows projected winter demand peaking across all of the 4 Platte River Power Authority communities with scenarios for high, medium, and low adoption rates of heat pumps. So what we see here is that even under a high adoption rate, that's the black line that we see here, it would only add a small amount, approximately 3%, to the demand by the year 2030. So what we're saying is within the next few years, there's plenty of capacity to meet the demand that electric heat pump technology would put on the grid. So I've titled this slide, "It Takes a Village." So a lot of work is being done on the utility side. And I want to provide a little information on really why it takes a community-wide effort and what that really means. So we estimate that replacing a single-family home's gas furnace with an air source heat pump whose electricity is 100% renewable could reduce emissions by 5 tons annually. That's one home, 5 tons annually. There's currently, to provide a little perspective, local perspective, there's currently around 60,000+ homes in the city of Fort Collins, and we're forecasting another 25,000 homes by the year 2040. So if even 1/3 of those homes were heated with air source heat pumps, we could realize an annual savings of 140,000 metric tons of carbon dioxide equivalent annually. So leaving you with that, I will now kick it off to Mike Missimer with MGI Mechanical to provide a little more information on different types of heat pumps and some of the pros and cons and things we need to think about. Mike, take it away.
Thank you so much, Brad. I appreciate it. And like Brad said, my name is Mike Missimer. I'm the owner and operator of MGI Mechanical Services, and we spend a lot of time installing and designing heat pump systems. I also have another company called Rockview Design, where we specialize in energy modeling and heat pump design, mechanical design especially. So, and like Brad said, I've been asked to kind of give a general fundamental overview of what heat pumps are and the different applications that we can find them in. A lot of people are heat pump curious. We're not going to go into a lot of technical data today, but we can definitely give a basic overview of what they are and how they're used. So, many people ask, what are heat pumps? Well, heat pumps are aptly named. They move or transfer energy from one place to another. We're essentially transferring energy either from the air or the ground or other means and moving it generally into a home or structure. It uses a compressor and liquid or gas refrigerant. Energy is extracted from the outside sources and then transferred indoors. The compressor pumps the refrigerant between 2 heat exchangers, and in one coil, the refrigerant evaporates at low pressures, which allows it to absorb heat. And when that happens, we can grab that energy. Then we essentially move it to the inside, where it's sent to a second coil, causes it to condense at a high pressure, and energy is released in the home. Next slide, right? So one of the questions I get from many people is, can I do air conditioning with a heat pump? Well, absolutely, they're reversible. This allows it to send energy into the home in the winter and draw energy out in the summer, which is nothing more than a standard air conditioner. So when we think of a heat pump system, it's essentially an air conditioner runs backwards. They can be used in a dual fuel application, which we'll go into a little bit later, with an air handler, or with an air handler, which is typically outfitted with backup heat source, such as electric heat strips. Next slide. So when we think of heat pumps, we generally look at 2 different types. The first type being an air source heat pump. And these are systems that essentially transfer energy from the outdoor air to the home or structure or away from the home or structure, as in air conditioning. So we are grabbing the energy from the outdoor air, transferring it to the indoors via refrigeration. And what happens with air source heat pumps, as the outdoor temperature goes down, there's less energy to move from the outdoors to the indoors. But our technology we have today allows us, in some cases, to operate down to negative 22 degrees. Now, it doesn't necessarily mean these are the best operating conditions, but in general, the high efficiency heat pumps can produce up to 100% capacity levels at 5 degrees. So technology's come a long way from what we were used to even just a few years ago. Next slide. The other type of heat pumps generally looked at as geothermal units Ground source heat pumps. These systems transfer energy from the ground to the home or structure. So usually has a loop field that runs underground, which has a water a system which is basically picking up energy from the ground, transferring it back to the house. Each of these systems have potential to provide comfort to the home using multiple methods. So people who do not have traditional duct systems can enjoy the efficiency of a heat pump. Geothermal systems are generally, can be more efficient than air source heat pumps, as the ground is generally maintains energy, maintains its temperature better than the outdoor air under extreme conditions. Next slide. So when we're looking at the different types of heat pump systems, we can use air source heat pumps or ground source heat pumps using a traditional duct system. And in these applications, usually with an air source, we have a couple different methods we refer to. One is called a dual fuel application. And just like it says, it uses two different types of fuels. Electricity is the primary source, and then usually natural gas or propane is a secondary. So it uses a traditional high-efficiency gas furnace in conjunction with the heat pump to condition a home. The gas furnace is a secondary heat source and takes over when the heat pump can no longer effectively condition the home. Now, some people set their heat pumps up, their gas furnaces up to, there's a balance point where it may be more economically viable to run the gas furnace than it is the heat pump. Really, it's a function of what are the energy costs of each fuel source at that point. Another application is all electric. It uses the air handler with backup electric heat strips. The heat pump will be the primary source of energy, but the air handler will energize the heat strips when the heat pump can no longer effectively condition the home. At some point, the outdoor air may get low enough to where the heat pump cannot condition the home effectively. So a backup source, the backup heat strips will then energize in conjunction with the heat pump to provide additional energy needed. And in ground source applications, they are usually all electric. These systems have backup heat strips in the event the heat pump cannot keep up. Now, heat strips are less likely going to be energized with ground source heat pumps because they're generally much warmer, temperatures are generally much warmer than the ambient air. So ground source heat pumps usually have better performance during low ambient conditions. Next slide, Brett. This is just a diagram of a traditional duct system. You can see down at the bottom, there's an air handler where we have a standard duct system like you would have on any furnace or air conditioning system. Next slide. We also have mini split applications. So mini splits are essentially small, compact air handling units that we can put in specific areas of the home, individual rooms. These units are very effective in situations where individuals do not have ductwork, specifically in all electric homes or homes with hot water heat. They are effective in those challenging rooms up over a garage or in different areas of the home that we have a hard time heating or cooling the space. The main advantages of the mini splits are they're small in size, flexible for zoning or heating and cooling individual rooms. Many models can have up to 8 indoor air handling units for 8 zones or rooms, connected to 1 outdoor unit. The number depends on how much heating or cooling is required for the building or each zone. Each zone generally has its own thermostat or control, so you only need to condition the occupied spaces, which can help save energy. These are typically inverter heat pumps, very efficient product. Next slide. This is an example of a mini split setup. So you'd have 1 outdoor condensing unit, which looks like a standard air conditioning system, where you could have many different variations of heads or air handlers or controls to different rooms. It shows one in the home office. That is an example of a cassette style mini split. Garage or hobby area, that's a high wall, another cassette. And in the children's bedroom, that's a ducted system there. It doesn't show the ductwork, but has a small air handler that will be mounted in an attic. Each one of these can provide comfort individually to each room. Next slide. Now, we're not set to just air source. We can also do domestic hot water and space heating. Hydronic heat pump applications. This application allows the user to heat up water for space heating and domestic water using either a ground source or air source heat pump. We've been very successful with these types of systems, very popular. Next slide. So retrofit applications, it's one thing to be able to design these systems from the ground up. That's, you know, at that point we're essentially engineering it from scratch. So there's not a lot to worry about. But when we get into a retrofit application, we have to pay attention to what we're looking at. We have to take into consideration some of the things that are out of our control. And one of those things is the existing distribution system, the duct system. And anytime that I go out and take a look at these applications, we always consider the duct system. So first thing I'm looking at is, can the distribution system support the airflow requirements in the new equipment? In general, heat pumps require more airflow than a standard forced air furnace. So we have to understand, can the duct system handle what we're wanting to do? So we have to take the time to test the duct system by measuring what's called the total external static pressure and the flow across the existing evaporator coil. It's really important that we understand the capacity levels. Then we have to understand, can the distribution system deliver the necessary energy to each room? Generally, heat pump temperatures, the delta temperatures are much lower than what standard air source gas furnaces are. So the delivery system is important. We want to make sure we're actually sending the energy where it needs to go. We always measure the output of the rooms, especially in the areas that we consider being problem areas. And then we also try to understand the leakage. The last thing we want to do is produce the energy at a very efficiently, just to have it to be leaking into the building cavity of the home or structure. So definitely want to look at those details. Next slide. Other things to look at from a distribution system. You know, duct system is just as important as the equipment design when considering it, looking at the overall energy efficiency and the delivery potential. Many people are dead set on putting in these high efficiency pieces of equipment, but if the distribution system is inadequate, it may not be a good fit. Inadequate duct systems can significantly decrease the equipment's ability to produce the energy or deliver it at the level it's designed to do, as well as create comfort issues within the home. Retrofit applications need to have special attention to the existing duct systems to ensure they're a good fit for the application, as heat pumps generally, like I said before, require more air than a conventional forced air system. Next slide. Another thing that I take into consideration is we have to understand the balance point, and we look at coefficient of performance of the heat pumps. And essentially, that's the approximate outdoor temperature which the maximum heating capacity of the heat pump matches the heating requirements of the home. So the balance point is when, right at the balance point is where the heat pump is essentially sized accurately for your home. Now, if the balance point is too high, if our balance point is up around 40 degrees, it may not make sense to put a heat pump in. We like to see our balance point down as low as we can get. If we can get down to 5 degrees, that would be great. But when we're considering using a heat pump versus, say, a gas forced air furnace in a dual fuel application, if our balance point is up around 45 degrees, it may not make sense to go with a heat pump, because at that point we're going to have to use the gas furnace as a backup or as the primary source, because the heat pump can't keep up. The cooler the outdoor ambient air becomes, the greater the heating needs are of the home. So as the temperature drops, the heat pump has a harder time absorbing energy from the outdoor air. This reduces the amount it can bring into the home. When the outdoor temperature is below the balance point, the heat pump needs help from a backup heat source, such as a resistant heater or a gas furnace. When the outdoor temperature is higher than the balance point, the heat pump alone can keep the home comfortable. So that's the goal, is trying to figure out a friendly balance point, one that's going to give you the best energy efficiency and best return on your investment. Next slide. This might be a little bit difficult to see. I added this later, but essentially this is just a quick graph of a balance point. So if you look at the blue on the bottom left-hand corner, when the outdoor temperature is below that certain point, the heat pump needs help from a backup heat source, such as resistance heat or gas furnace. Over on the right-hand side, when the outdoor temperature is higher than the balance point, the heat pump alone can keep the home comfortable. So the balance point is essentially the point at where the load on the house and the capacity level of the equipment match. And in this case, it's 30 degrees. Anything below 30, this particular heat pump would need additional help, a backup source. Anything above 30, this heat pump does just fine. So the goal is to get that balance point as far down to the left or close to 0 or 5 as we can. And we can do that by using higher efficiency equipment, or first and foremost, making sure that the home is insulated and air sealed right, so it's maintaining those energy levels and we can reduce the load. Next slide, Brett. Other considerations we need to think about, so size and energy of the home. In some cases, the size of the home can be a deterrent. Many large homes are conditioned by a single system where a single heat pump may not be able to adequately handle the load at low temperatures. The return on investment is not there, as the backup will be much more, which will be used much more than we would like. We have a scenario where we have this right now. The individual is still going with a heat pump system, but he's got a great big home. It's nearly 6,000 square feet with a single heating system in it. And it's difficult to be able to properly condition his home with a single heat pump system. They just don't have the capacity levels. I should say, a single residential system doesn't have the same capacity levels as some of the larger gas furnaces out there. Other things to take into consideration are the electrical service. In some cases, the home just doesn't have the adequate electrical service or load to handle the equipment. And in some cases, it can be cost prohibitive to upgrade the electrical service. So that's another thing we really need to consider when we go into it. Is there enough usable power available to provide and install a heat pump system? And then the overall energy efficiency of the home. Some homes really should have energy upgrades, such as insulating and air sealing, to show a solid return on investment. Due to, in some cases, the large expense of a heat pump system, they are not inexpensive pieces of equipment. However, installed properly, we do see the solid return on investment. But in many cases, as much as I'd love to go in and provide a heat pump for people, ultimately the first thing they should do is upgrade the insulation, air seal a home, and try and reduce the load on the house. Next slide, Brett. So then we talk about some of the pros and cons. All right, so pros. Heat pumps typically have lower running costs. And a lot of it's as a function of what are you comparing it to. Now, right now, natural gas is very inexpensive. However, we're probably going to see that change in the future here. When we're comparing it against fuel oils or propane, it's a much different situation. They will generally, in all cases, have lower running costs. They generally require less maintenance than combustion systems. They can definitely be safer, no gas or carbon dioxide output, so we don't have to worry about that. Lower or no carbon emissions. Now, obviously, we're going to have some carbon emissions with a dual fuel system, but if we can get that balance point down to a very, very low temperature, that gas furnace may never even fire. The inverter technology can be very quiet, as these systems will modulate up and down based on the demand. And if we generally, when we take these systems, we set the thermostat and leave it. If we're under standard conditions, they'll just purr along at a very low rate. And then one system can provide heating and cooling. We don't have to have multiple components in many cases to do the same thing. Next slide. Some of the cons. Heat pump cost for installation can be expensive, but it's like anything else. There's multiple tiers of these pieces of equipment. You don't have to buy the biggest and the best out there, so they come in many ranges. They can be difficult to install. It takes a company that knows what they're doing, but you also have to do the research on the front side. When I say they can be difficult to install, it's really considering taking into account the front end considerations that we have to do. they can struggle in extremely cold temperatures. But I ask, how often are we really there? How often are we truly at sub-zero temperatures in Colorado anymore? So generally in our climate, they're an incredible, great fit. They may not be good a good fit in every application. Like I said before, if we have a compromised distribution system or a very, very leaky shell, or we don't have the power, we don't have the panel, enough power, room in the panel to be able to provide adequate electrical load, then they're not a good fit. They do require more air movement than a traditional furnace. And one of the things, you know, people, some of the feedback I get is they tell me, well, the air feels cold. Well, it doesn't feel cold. It's not 120 degrees like a conventional gas furnace might be. It might be 95 or 100 degrees, but it definitely feels cooler. High efficiency furnaces average around 200 cubic feet of air per 10,000 BTUs of output, where heat pumps will average around 400 cubic feet of air per 10,000. Essentially, that reduces the air temperature coming out of the vents. So something that we try and educate people on before they invest. And I think that was it.
That is it. Yeah, thank you, everybody. We got through that pretty quick tonight. So I think this is a great opportunity for us to take questions from the group, and hope we can have a good number of questions and a good discussion. So feel free to ask away.
Okay, well, first question was just a quick comment. PRPA also has well, a 90% carbon free, or over 90% carbon free by 2030. So and then carbon free by 2050. So we do have, just a comment on your earlier slides. Here's another question, I think, regarding your carbon emission slide, Brad, is are you including personal autos as well as commercial transportation in that?
That does not include that, no.
So was it just building carbon?
Yes.
Or, okay. Next question. Please explain what when you were talking about efficient to 5 degrees. Could you explain that in a little deeper detail?
I can provide I can jump in and give a little overview on that, and then Mike can kind of chime in as well and provide a little background information. But there's really what's called the coefficient of performance. So Mike mentioned in his presentation there's a COP associated with these heat pump technologies. So the coefficient of performance is really kind of a measure of how efficient that appliance is at a temperature. And a lot of the cold climate heat pumps that are available today have a coefficient of performance of 2, roughly 2, and some even a little bit greater than that at 5 degrees. And really, I think, and this is kind of an overview, but a 2 is roughly double the efficiency of a gas-fired appliance. And Mike, you can correct me if I'm wrong on that, but kind of a general rule of what we say. So as the temperature goes down, as we dip below 0, that coefficient of performance then starts to slide downward, and we get less efficient in the equipment. So, Mike, if you want to add anything to that, jump in.
Mute. Yep. Absolutely. So, like we talked about, let's talk about heat pumps from 20 years ago. So generally, you know, heat pumps had a bad rap for a long time. People said they didn't work in our climate. And non-cold climate heat pumps, they may not be able to produce the energy we want to condition our home down below a certain temperature. Our switchover point, our balance point, was usually around 30 or 40 degrees before, simply because it became either more efficient to run the gas furnace, or the heat pump just couldn't keep up. Today's cold climate heat pumps have the ability to produce 100% of its rated output or rated output at 5 degrees. Like I said, some heat pumps can operate all the way down to -22. Now, they may only be able to produce 40% of what their rated output is at -22, or even 30%. But the reality is we can get in some cases, 100% of our rated output all the way down to 5 degrees. And when we consider our COP, I mean, essentially COP, when we consider our power output in kilowatt hours or in kilowatts, if we have a COP of 2, we can essentially produce 2 kilowatts for the price of 1. So if we have a COP of 5, we can produce 5 times the energy as we would with standard resistance heat. So 1 BTU or 1 watt gives us 3.41 BTUs. If we have a COP of 2, 1 watt will now give us 6.82 watts, or BTUs, I'm sorry. So essentially, our COP as it goes up can essentially double, triple, quadruple, or even quintuple our total energy production that we would have under normal circumstances. Straight electric heat, for example, very expensive heat when we consider baseboard electric heat. 1 watt, again, yields us 3.41 BTUs. If we have a COP of 2, we get 6.82 BTUs for every 1 watt of energy we buy, if that makes sense. So when we explain it, when we say they're efficient down to 5 degrees, that's when we take a look. I analyze the home. We determine what the good balance, what a balance point would be for that home based on the load and the loss and gain on the house. So long story short, these heat pumps, very efficient, very effective in comparison to yesterday's. And if we can produce 100% of the energy at 5 degrees, we're doing pretty good.
Okay, good. Next question. We have many homes with only 100 amp service. Can we upgrade these homes at a low cost, i.e. not requiring expensive service upgrades?
Ooh, Mike, you want to take that? I can kind of jump in and provide a little context on what we're seeing in the city of Fort Collins. But for the most part, a lot of the service that's now provided to new construction homes in Fort Collins starts at 150 amp service. Builders and developers do have the option to install 200 amp service, but as a lot of you probably are aware or know, there are a lot of older homes that have 100 amp service. So 100 amp service, I think might be pushing it a little bit, especially as you start to electrify other appliances, and especially if we look to add things like electric vehicles into the mix down the road. That's something that we're having to explore within our utilities light and power capacity and fee structure as mentioned earlier. So how do we encourage people to move to 200 amp service to accommodate future electrical needs? So things we're discussing, but I would say in general 100 amp service, I think you could still do it, but I think there could end up being some challenges. If you have everything running all at one time, certainly there's going to be issues.
Okay, next question, probably for Mike. We have an older 2007 dual fuel heat pump system. It seems the furnace is running all of the time when heating. Is the heat pump just a supplement? Mike, are you there?
Oh, he just messaged me. I said, I think I lost you guys.
Okay,
so,
we'll give him a...
Yeah, we'll see if we can get him back on. I think it depends on how and when you see that piece of equipment running. Certainly, the equipment today is designed to run, especially at design temp, run for long, have a long cycle time, so a long run time. On an older piece of equipment like that, it could just be that we've reached that capacity at temperature and it's running for a longer period of time. But that's definitely more of a question for Mike. So let's see if we can get him back on here at some point. So.
Well, while we're waiting, where are the heat strips located? Within the air handler as radiator panels?
They are. That's exactly it. So it's within the air handler itself. I wish I had a picture of kind of what they look like, but within the unit, yes.
Okay. Okay. Got a two-part question here. Given the costs of drilling, potentially cut down by the 26% federal tax credit, when, if at all, does it make more economic sense to install a ground source geothermal as opposed to an air source heat pump system?
So I think economics are tough, and you certainly have to look at the price of drilling those wells, whether they be horizontal or vertical. There has been a significant reduction in the price of what it costs to drill geo wells, but there is that additional expense. I certainly wouldn't want to answer that with any other way than it's something that you would have to explore. You know, there's lot considerations, certainly access to get the equipment in there, and any number of things. So, and I just did get a message from Mike. He's trying to jump back on right now, so hopefully we get him in.
Is there anything renters can do to electrify their heat efficiently?
Wow. Well, I guess you know, maybe speak with the management company or the owner and see if they could pursue one of our city EPIC programs to improve the efficiency of the building. So we do have a program in place to work with landlords and owners to improve efficiency of the units. But in general, you know, the system is what it is, and the building probably is what it is. So likely very little you can do, you know, without spending some of your own money to improve the efficiency of the system.
Okay, what about integrated system for space cooling, space heating, water heating, clothes drying, all by sharing heat among each other?
Oh boy. Probably not a question I would be comfortable tackling right now. I think there's always, you know, some people trying to integrate certain things within, you know, the options. I know, you know, take for instance, heat pump water heater. You know, you're dumping a lot of cool air once you extract out of the indoor environment. So certainly there have been discussions on, could you, instead of ducting that to the outside during the summer months, you know, maybe, you know, duct that to the inside somehow and things like that. But I'm not aware of too many of those integrated systems right now. We just don't see these types of systems being installed. So I don't know about the viability of them.
Okay. How efficient would a heat pump be for a retrofit for a hydronic baseboard heating system that operates at 140 to 150 degrees Fahrenheit? That's probably a Mike question. Unless you...
He just messaged me. He says back in. So are you seeing him, Pete?
Yeah, he should be. I think he's connected. It says he's connected to audio. Mike?
Can you hear me?
Yep.
Okay. Trying to play back up. Sorry, guys. I'm not sure what happened. I got kicked off, so I logged back in a different way. So.
Okay, no worries. So we've got a pretty technical question,
Sure.
and I'll probably repeat that earlier one when you dropped off. How efficient would a heat pump be for a retrofit hydronic baseboard heating system that operates at 140 to 150 degrees Fahrenheit? Are you still there, Mike?
Yeah, I'm not sure what's going on here. I apologize here. We do have heat pumps. There are cold climate heat pumps out there that do have the ability to produce water of those temperatures. Now, again, in some cases, it depends on if we're using ground source or air source heat pumps. Sometimes we have to use a supplemental flash boiler, something to help give it a little bit of a little boost in the event that we are dealing with an extreme temperature. Much of it has to do with either the loop field or the outdoor design temperatures. But we do have, generally we see heat pump design hydronic applications more in-floor where water temperatures are lower, around 120 degrees. But we can produce temperatures 140 degrees. Arctic heat pumps out of Colorado, as a matter of fact, have some of the incredible product that they are advertising. Now, I haven't seen this personally, but advertising up to 170 degree water output under certain conditions. So
Very good.
It's doable.
Okay. So next question. Mentioned in the retrofit section, what is meant by heat pumps need more air than a fossil fueled furnace? I think that was the air movement, the airflow through the ducts, right?
Absolutely. So when we measure output of a heat pump, we measure it in tons, just like we would do in a standard air conditioning system. So when we consider tons, we say, what does that mean? Well, when we think about it, nice Jeopardy question here. It takes 12,000 BTUs of energy to melt 1 ton of ice in 1 hour. So essentially, a 1 ton heat pump has the ability to produce, in general, 12,000 BTUs. A lot of things you would take in consideration, altitude and D-rate and different things like that. However, for every 12,000 roughly BTUs we produce, we need to move approximately 400 cubic feet of air across that evaporator coil to be able to effectively do that. Or we run the risk of running into pressure challenges in air conditioning. We see frozen coils, etc. A gas forced air system may only need to move 200 cubic feet of air to produce for the same 12,000 BTUs or 10,000 BTUs. And essentially that's why the air feels so warm when it's coming out of the vents when you have a gas furnace. We may have 70 degree air moving across the heat exchanger, into the burners themselves, and then when it leaves the heat exchanger, we may have 120 degree air. So we may have a 50 or 60 degree temperature delta. Where heat pumps are moving more air, we don't see that same delta. It may only be 90 or 95 degree air coming out of the vents. So that's essentially why we need more air. Just the dynamics and the physics of moving the air across the evaporator coil and what we need per ton of output versus every 10,000 BTUs of output on a gas furnace.
Okay. Next question here. Is there a rule of thumb on the maximum size of a housing unit? Can heat pumps be configured equally well for single family homes as well as multifamily units? And then the third part of the question, to what extent does absence of qualified workforce prevent adoption of this technology? So first is a rule of thumb on square footage or maximum size of a housing unit.
Well, I mean, there's always rules of thumb, but to properly analyze whether or not a heat pump's a good fit, you have to go in and do a manual J load analysis. You have to do a little bit of research on the property. It's nice if we can have blower door information, infiltration information, but essentially the size of the house, the size of the heat pump is going to be determined on what the heat loss requirements are of that home. Let's take today's standard. We may be able to utilize a single heat pump system for homes that are, north of 5,000 square feet by today's building construction. But if we take that same building that was constructed, same size building, maybe constructed in the 80s or even in the 70s, the assembly is going to be much, it's going to be less than what today's standards are. It's going to be, by definition of today's standards, very leaky, and we may not be able to produce this. We may not be able to effectively heat that home. So it's difficult to say, is there a general rule of thumb or size? Some people may say yes. In my world, no. We have to analyze the home and determine what we need. Single family and multifamily, it doesn't matter. It's understanding the loss and gain on the house. The nice thing about today's technology as well is we have what's called inverter or modulating technology. So these units can start out as low as 25% capacity and then ramp themselves up in 1% increments all the way up to 100%. So sizing these are much easier today than they were yesterday. We can even have a little bit of an oversized application, which isn't going to necessarily hurt the home because the system will just run at a lower rate generally. Hopefully that answers the question or helps.
Okay, and then the last one, to what extent does the absence of a qualified workforce prevent adoption?
You know what? Honestly, we've been pretty fortunate. I think I'll put it this way: it is tough to find qualified people at this point. Definitely is, but there are definitely still qualified technicians out there. Personally, we haven't had too much of a problem. We have a lot of in-house training that we do with our technicians to make sure that they are supported and have the tools and resources they need to perform out there. So hasn't been so bad.
I'll chime in a little bit, Peter, too, and just provide
Sure.
a little background from our the third-party consultant study that we had done. There were some findings that we heard from some of the contractors that took part in the study. There's a lot of familiarity with it, is what we heard. They are aware, they're familiar. They did admit to being maybe a little biased or self-selecting on it. They also noted that they really do truly have some challenges, and they need training on how to do commissioning on these things. So there is a little bit of that in the workforce, no doubt. It's something that I think we'll look to maybe partner with some organizations and certainly some contractors like Mike with MGI here, and to kind of maybe spread that a little bit throughout the community and maybe do some more contractor specific training. So we're going to continue to do some outreach with them and make sure that if there are resources that we as the city can provide, training resources, that we'll look to do that.
And you know what? Maybe I should expand just one more little bit on that. I think the mechanical contractors out there that believe in the product, that choose to look at heat pumps as a viable resource, will educate themselves. There's still a lot of people in the industry that, unfortunately, they're not on board with the technology. They still think of yesterday's technology, and they consider the gas furnace to be the means. And some people just aren't on board. So I would suggest to the general public that if you are considering heat pump, make sure you understand the contractor that you're considering. Ask the right questions and just make sure that you've got qualified individuals out there. And I'll tell you, most contractors who don't believe in heat pump technology, they'll say we don't do those. Anyway, there are many great contractors out there, and like Brad said, I think looking at the energy providers list of qualified contractors can be a good guide for people out there.
Great. Next question. If I have a standard gas furnace plus AC, can I replace the AC with the heat pump and then use the furnace for backup?
Absolutely. That's an ideal situation. That's called a dual fuel situation. And generally in those cases, you do not need additional power supply. Sometimes the heat pump may draw a little bit more amperage, so a breaker may need to be changed. But again, some considerations need to be made. You got to take a look at can the distribution system support the heat pump, and 'cause usually what you're going to find, sometimes we see air conditioning sizes when we retrofit them, they actually go down. We as HVAC contractors have been amazing at oversizing equipment for a lot of years. So as we learn more about what we're doing, we're realizing that this was a problem. So it actually helps us a little bit in this case, because in most cases, what I find is duct systems are sized adequately for the heat pump technology. But yes, you absolutely can do that.
And just to add to that, my supervisor chimed in, and it is something that we're looking to expand our utility incentive offerings for those exact type of systems in the future. So maybe something coming around the corner.
Explain the 400 cubic feet of air versus the 200, unless I think we answered that, but it's just the matter that the air source heat pump just has to move more air, twice as much air as a gas system in order to effectively move the same amount of heat.
Correct. We're using a different method. Instead of heating up a heat exchanger and pulling the energy off of the heat exchanger by moving air across it, we're essentially moving air across a condenser or evaporator coil. And when we do that, it just requires us to move more air across that airside device, across that coil, than we would across a standard heat exchanger. It's the physics. It's the physics of the product just requires us to move more air. And that is one of the nicer things about a gas furnace is one of the complaints I used to get with heat pumps, especially with a single stage heat pump that just comes on full blast and then shuts off when it's done, is people didn't like the noise. They didn't like the cold air temperatures. But the new heat pumps, like I said, they run their inverter. They have modulation limits to them. They have the ability to run at a real low capacity and all the way up to full capacity. So the drafts that people were accustomed to with heat pump technology are reduced. But essentially, it's just the heat pump needing more air to move. It's the air conditioner is the same way. We need to move approximately the same amount of air across the heat pump as we do the air conditioner.
That's a great analogy. All right. When will we see heat pumps with low greenhouse gas refrigerants, not R410A, for example?
I don't know. I mean, I think there are technologies. There are different products on the market. There's not the mainstream products are all using standard refrigerants. So R410A is the alternative to R22, which was generally used in most residential refrigerant applications. R22 is a chlorofluorocarbon that has a chlorine molecule, which is the ozone depleter. R410A is a hydrofluorocarbon, does not have the the chlorine molecule in it. But at some point, different drop-in refrigerants could be used. R454B, for example, may be used. But at some point, the manufacturers, as the compressor manufacturers start to switch over, and as different manufacturers test the products, I'm sure we'll start to see them be available. But we are not hearing, at least from the big box producers out there, that we're going to see, anything anytime real soon.
Okay. I've installed solar, new windows, and insulation. Help me rationalize the cost of adding a heat pump now rather than waiting for my furnace hot water heaters to fail.
You want to take that one, Brad?
Well, I'll certainly start with there are incentives for heat pumps right now, depending on where you're at. Within the city of Fort Collins, we have our Epic Homes program, which does provide incentives for heat pumps. So that can kind of help bridge that gap in expense. It sounds like at this point, yes, you've done a lot of the right things, and really it's almost just like an eco-conscious decision. So the systems do work in town. Mike has some stories that he could certainly tell. On some of the systems that he's installed recently, and even one of the stories he told me today, we got a system that's outperforming what they expected it to even do. So the technology is there, the systems work. I think you have to kind of weigh the incentives. So maybe explore City of Fort Collins Epic Homes program, see if there's a rebate that might tempt you a little bit. And then, of course, just have conversations with the contractors and then run the numbers and see if it makes sense. So, and of course, you're benefiting the climate. You're lowering your, one house's greenhouse gas emissions. And I had that slide earlier. So, you could be looking at, lowering your greenhouse gas emissions by 5 tons annually if you do that. So.
Okay, next question. I have an older 12-year-old ground source heat pump with a break even probably around 25 degrees. Do they make newer cold weather or more efficient units that might get my break even down further down, assuming good insulation, no duct leaks, etc.?
Absolutely. One of the presentations that I've done in the past is talk about balance point and ways to lower your balance point. And there are essentially 3 ways there's multiple ways to lower a balance point, but 3 major ways to change your balance point. One is larger equipment. Obviously, bigger is not always better, but again, we're dealing with inverter stuff. So larger equipment generally has the ability to produce more energy at lower outdoor temperatures. But you got to note that duct sizes may not be able to handle the larger equipment. Then secondly, we have, cold climate inverter heat pumps. They are much more efficient than yesterday's models. Inverter and low ambient heat pumps can generally produce more energy at lower outdoor temperatures. And obviously the third way is tightening the envelope of the home. So here's an example, an example of a piece of equipment, and this is one of the ones that I talk about here. An example of a standard 3-ton single stage, call it Payne 3-ton heat pump. For example, this particular unit at 10 degrees, at 60 degrees, it can produce 40,000 BTUs. But at 10 degrees, it can only produce 18,000 BTUs. But then if you compare that to a new 3-ton inverter cold climate heat pump, at 60 degrees, they still produce the same 40,000 BTUs. The major fundamental difference is at 10 degrees, the inverter will be able to produce 30,000 BTUs, roughly double than what the older single stage units can do now. So that's a big difference between today's technology versus yesterday's. So if you've got one of the older pieces of equipment, we would have to look at the engineering data to see what it's capable of producing at low ambient conditions and compare it to the new product. But in this case, if we compare, say, a Carrier 3-ton inverter cold climate heat pump at 10 degrees versus a Carrier 3-ton single stage or Payne 3-ton single stage, almost double the output at 10 degrees and essentially the same output at 60 degrees. So major difference is the colder it gets, the better we produce.
Okay. Question for Brad. Is Fort Collins Utility examining ways to expand financing to homeowners and renters, like on-bill financing or pay-as-you-save?
We are, and I think there'll be some additional offerings coming out soon. I did kind of mention, the exploration of incentives for the dual fuel heat pump system. So these are all things that we're having conversations on and we're looking to implement in the next year or two. So absolutely.
And those are all through or going to be through Epic Homes, right? That's pretty much everything is bundled there as the one-stop shop, correct?
That would be correct, yeah.
Okay, I assume that a heat pump must be kept clear of ice and snow. How can this be accomplished other than having to get out in the middle of a blizzard to clear the heat pump?
Oh, well, from an installation standpoint, you want to keep them from generally you want to keep them away from any spot that's going to drain water down on top of them. You want to try and keep them in an area that we're not going to see the ice and snow build up as much. Now, we have blowing snow. We have 40 plus inches of snow, or even 50 inches in some cases with these spring storms. We usually don't see heat pumps being completely covered up in snowstorms unless we get an excessive amount. They usually set up on a platform that's at least 12 inches off the ground that allows them to shed water when they go into a defrost mode. I think Brad mentioned in his presentation that when they run, they will produce, they'll start to build up with ice. So they go into a defrost situation. They'll essentially run backwards and run the air conditioner and melt the ice off. So we set them up on a tall platform or pad that allows it to shed the water. So under most conditions, even with snow like we had today, you won't see the snow covering them up. But I have seen, especially when the heat pumps are set on the north side of the house, blowing drifts where people have had to go outside and brush them off. So that is definitely a perk of living in Colorado.
Yeah, and I can, Peter, we did a heat pump workshop a few months ago in the city of Fort Collins, and we had Sean Lamont from Mitsubishi Train come and present, and he had some examples in one of his slides. So if you'd like, I can kind of share my screen of what some of these screens look like and what some of the racking look like, to elevate that. So if you don't mind, yeah, I'll just really quickly share my screen to make sure everybody's seeing the right screen here. So hopefully everybody kind of sees what this looks like right now. But this is some options that he's seen and pictures that have been sent to him from out in the field. So.
And in the top left corner there, these are called side discharge units. So typically Mitsubishi or mini split systems are side discharge. Many of the big box carrier, Lennox Train, they'd be a top discharge. So you wouldn't want to do options on the left there, covering them up. At that point, you could hurt the performance of the system. But there are ways to keep the snow off, and you can see just about every one. The one up on the top left corner is sitting on the ground. That's not standard application, but you can see the stands that the other ones are sitting on. That's typical application, or even hanging them from the side of the building.
Okay, next question. How does the price of a heat pump compare to a gas furnace for new construction, like people rebuilding after the Marshall Fire? And obviously your heat pump would also replace your AC unit.
Heat pump technology can be more expensive than a standard gas furnace and air conditioner, especially when we're talking about the inverter pieces of equipment. Most of these pieces of equipment are communicating, which mean they use a little bit better technology. One of the benefits that people have are some of the rebates that are available. Many utilities companies out there providing rebates to help offset the front-end costs of these pieces of equipment. And one thing that I think people really need to try and understand is, and this is what we forget about, these pieces of equipment are one of the few pieces of equipment in your home to send you a bill every month. We have to try to consider what our return on investment is. And, depending on what we're comparing it to, you can see a very quick return on investment, depending on the rebate potential. and also, what you choose. So I would say be prepared to spend more money on the front side with the overall hope and end result that you're spending much less on the back side. And if you can offset it with rebates, such as the Efficiency Works program that Fort Collins Utilities is part of, or Excel, there's a lot of money out there to be. In some cases, heat pump systems, we have a promotion right now where people are getting up to $3,000 back in either rebate money from the utility company or the manufacturer themselves. So that's a pretty good deal.
Okay. How can we go about getting a home assessment to see if our house is a good candidate for switching from forced gas to a heat pump system? And they're in Lafayette, Colorado.
That's probably within Excel territory, so I would certainly say reach out to your utility provider. Excel does have an assessment program and rebates, so that would be the first place to start. If you were in Fort Collins, I would direct you to our Epic Homes program, which is fcgov.com/Epic Homes. There's an area on there where you can find out rebate information. You can schedule an assessment, but most utility programs have some sort of program like this in place.
Okay. What amp service would be required for a typical heat pump application? For a typical application, I have 150 amp service and a 2,600 square foot house.
So if we're talking a dual fuel application, your air handling or the gas furnace would just be 120 volt, typically a 15 amp circuit, and the heat pump itself generally won't need anything above and beyond what your air conditioner is now. Now, 2,600 square feet. Okay, let's use a general rule of thumb. Let's just say you needed a 3-ton heat pump in there. I'm throwing a dart. You're probably going to be looking at a 40 amp circuit for that outdoor condensing unit, depending on the product that you choose. And there would be no electrical upgrades to the indoor air handler if you decided to go with a dual fuel system that was just standard gas furnace. If you chose to go with an air handling system with backup electric heat strips, now you'd be looking at an additional 208, 240 circuit with potentially up to a 60 amp maximum overcurrent protection. That's where it really starts to grow. That's where things jump up. If you go with that all electric backup component, because of the heat strips, they do draw a lot of energy when they do in fact run, or have the potential to draw a lot of energy. Let's put it that way.
Okay, well, kind of a similar, have you had good successes adding heat pumps in older homes, so general retrofit?
Absolutely. I'll give two examples. One example, the house was built in early 80s, and I wouldn't say this is an older home. This particular house had minor upgrades to it, a little bit of insulation. They put some solar on it. By today's definition, it's a leaky home. It's a pretty standard home. These particular clients wanted no gas in their home. We ended up tearing the gas line out of their home, as a matter of fact. We put an air handling system with electric backup heat strips in it, with a heat pump water heater in there as well. And as I was telling Brad earlier, it was about a year ago. I couldn't sleep. And the nice thing about these these pieces of equipment too, is I can monitor some of them from my home computer. So this particular homeowner wanted to lock his heat strips out at 5-degree outdoor temperature, and I thought, well, that's dangerous. But I said, why not? Let's try it. I believe it was about 2 o'clock in the morning. It was roughly 8 degrees outside, and I decided to log in and see what was happening with our heat pump. And it was maintaining 68 degrees in the house, running at 36% capacity. So I would say that's an incredible success. And I was scared to death. I thought his balance point was going to be somewhere around 10. This particular heat pump was producing enough energy to maintain 68 at 36% capacity. It still had an additional 62% of drive that it could potentially push. So that was a great success. And another one, this house was built in 1905. Now, these people did add some insulation. It's not a very energy efficient home, but they've had no problems whatsoever. They do have a dual fuel system. I checked in with them the other day. Because of the insulation upgrades they had done, he told me it transfers over to backup gas about 5% of the time, and that's just under extreme conditions. So we've been very happy with the success. But again, you have to do your homework. You have to make sure the situation's right.
Okay. Here's another case study. I have a 1,200 square foot single story home over a crawl space. Can that ground be used for ground source? Also, I like to have a warm house in the winter. Can I keep the house at 72 degrees? So kind of two questions there.
I've never drilled a crawl space before. That would be difficult. Generally, the loop field in a ground source heat pump, you would be looking at probably in a standard residential situation, be looking at what's called a vertical loop field. And the nice thing about these loop fields is we only need about 15-foot separation between loops. So I would say a 1,200 square foot house properly insulated on crawl space, we probably wouldn't need any more than about 3 loops. And can you keep the house at 72 degrees? Absolutely, you could. The heat pump would easily be able to produce that, no problem. And then in the event that you did run into extreme circumstances, the electric heat strips, if they needed to kick on, they could. So ground source heat pumps are a little bit trickier because we have pumps and we have manifolds and we have different things that we need to bring into the home. But, it really be a function of taking a look at what you have. Trying to drill a loop field through your crawl space, though, would be, well, I don't know how they do it. To try and get a drilling mechanism down in that area would be impractical, probably. So.
Yeah, I've seen some smaller drilling mechanisms now. They can easily come into a front yard or a backyard or a side yard and do it. But really, those vertical wells are going down. Those loops are going down 200 to 300 feet. So there's a number of pieces of drill equipment that would need to be fitted to get that kind of depth. So the other thing would be, of course, the horizontal, like was mentioned, but a crawl space would not be nearly large enough for a horizontal loop field. So it would take up a much greater piece of real estate.
Okay, a comment from one of my fellow CRES board members who has a Mitsubishi Hyperheat line unit with 92% rated output at -13. The one in his house was producing 95-degree air with an outside temperature of -25.
Excellent.
So there's some.
The
technology is definitely there.
Yeah, it's kind of busting the myths. We hear it all the time. And, when I talk about heat pumps to people, almost always the first response I get is like, well, you can't heat your house when it gets below 20, 30 degrees. So they do work, especially the new pieces of equipment today. Absolutely.
Okay. Sorry, a long question here. So it appears that retrofitting existing homes that are poorly insulated, leak air, have poor forced air delivery systems would be very expensive to upgrade with better insulation, improved air delivery systems, etc., or poor candidates for heating with a heat pump. However, since 20% of the gas used in the home is to heat hot water, would it seem to make good sense to encourage owners to replace their hot water heaters with heat pumps? And do you agree? And if so, what should we do to encourage the replacement of gas hot water heaters with heat pumps? So if you can't do your hot air, at least do your water, I guess is the the question.
Well, everything has an application. They have pros and cons and application issues. We love heat pump water heaters. We've been installing a ton of them. One of the downsides to a heat pump water heater, and I think I heard Brad say, is they reject cold air. They're basically taking warm air from inside, transferring it to the water, and as a byproduct, we get cold air output. So we have duct kits that we attach to many of these systems that we have the ability to push to the outside. I think a heat pump water heater in the right application is perfect. But again, some of the cons of a heat pump water heater is if we don't have the ability to duct it to the outdoors, it can make a room or rooms relatively cold that are close. And then there are some restrictions. Generally, heat pump water heaters need a certain mechanical room size so they can effectively reject that cold air without recirculating it. If we take a heat pump water heater and we put it in a small mechanical room and we drop the air temperature of that room from 75 to 60 degrees, we don't have as much energy in the air to transfer back to the water. So we can effectively or essentially reduce the capacity levels of that heat pump water heater. So, if your goal is to, reduce overall gas usage and the heat pump water heater does give you it's a good fit for your home, then absolutely do it. You can assume though, you're going to have to add about a 30 amp circuit, a 208 to 240, 30 amp circuit to where that heat pump water heater is, where a standard gas furnace water heater, if it's just a natural draft appliance, has no electricity to it.
One thing to just add to that, Mike, I don't know how much of this you've seen yet, but there are rumblings that they are coming out with lower amp service heat pump water heaters in the future. So
I'm looking forward to it.
Yeah, the majority of them are, you're likely going to need that 30 amp service, but I think they're coming out with, I don't even know yet. Kind of looking it up right now to see if there's any offerings. So.
Well, part of what it is, Brad, it's the 4,500. Most electric water heaters are 4,500 watts, and in the heat pump water heaters not only have the heat pump, the compressor element, there are two heating elements inside of them as well. So, in the event the compressor fails, it can go to straight electricity, or in the event that you overwhelm what the heat pump's ability to produce is, it can go into what's called hybrid mode. So instead of using 100% heat pump, it uses a combination where it'll use the heat pump itself to produce the hot water needed, but if you exceed what the heat pump can produce, then it will energize one of the two elements or both the elements to help satisfy the need. And I think that's where that 30 amp circuit in general right now is being primarily utilized. And I have heard that, and I think what they're doing is considering dropping down to say a 2,500 watt backup versus the 4,500 watt full capacity.
Okay, next question. Thanks for the nice presentations. I want to emphasize that the retrofit of existing homes, the super insulation and air sealing will make the cut for the load on mini splits. In my house, I put in 3 mini splits with SEERs of 42 and 33. The heating performance HSPF were up to 15. These make the 40-year-old home very comfortable down to minus 20 degrees outside. So again, emphasizing the importance of your envelope when you're looking at the retrofit. So that was more of a comment. Can you talk about the process of doing a retrofit? Specifically, how would a heat pump be combined with the forced air furnace? Assume you have to combine the output of the heat pump into the duct system. How is that done? Are there problems, in siting the heat pump? I guess locating the heat pump.
If you have air conditioning that exists today, it's very simple. if we were looking at a dual fuel application. Essentially, we're taking out the outdoor unit component of the air conditioner. We're taking out, and usually the furnace is replaced as well. We do have ducted mini split technology we use in conjunction with a 24-volt user interface that allows us to couple a inverter heat pump, cold climate inverter heat pump, with essentially almost any air handler out there now. Now there's downsides of that we don't get the same modulation limit or modulation potential on the fan. But to get back to the question, it's very easy. The consideration is this. Let's say, for example, you have a 80,000 BTU furnace in the home now and a 3-ton air conditioning system. In general, we're going to be moving somewhere in the neighborhood of 12 to 1,300 cubic feet of air effectively for that system to operate. But if I came into the house and said, okay, we need to size your home for heating for the heat pump, we need now a 4-ton heat pump to be able to effectively heat your home, we are now going to need to move somewhere in the neighborhood of 1,600 cubic feet of air. At that point, I would be analyzing your duct system to determine whether or not that duct system has the ability to do it. So as long as the duct system has the ability to allow the air handling system to move the air, it's very easy. So in general, if you already have air conditioning, it's pretty simple. When it can get complex is when we go to a straight air handling system with electric heat strips. Can we get the electrical down to the system? Or in the event that you don't have any duct work, at that point we'd be looking at a non-traditional method such as the mini split. And the biggest challenges we have with that is how do we get the refrigerant lines from the air handlers themselves back to the condensing unit. So overall, the install is relatively easy. The hard part's just setting it up. These units, what you have to remember, are not turnkey. We can't just slap them in and turn them on and walk away and expect them to function. We have to do a full commissioning process with them.
Okay, here's a question I was expecting. Did the regional load analysis take a look at the extreme situation where we have minus 20 degrees for 3 or 4 days like we did in 2017 or 2018? What happens if all the heat pumps switch over to electric heat strips?
Yeah, I think all I can say on that is it was weather normalized in that analysis. So remember going back to that original slide of like, is the capacity there, like in the city of Fort Collins? And assuming we, at this point, even, widespread high adoption, we would still have the capacity. If we continue on this path of like, if you end up with, 60,000, 70, 80, 85,000 homes all electric, and we haven't made any adaptations to the grid, then absolutely there's going to be some issues. The key to that is the study that we commissioned is showing that, even at a high adoption rate right now, we're not looking at any issues until probably well past year 2040. So yes, there are concerns, certainly, but right now we have time to figure it out, and we can act from now, until 2030, and that's even assuming we get, a high adoption rate in this, and that's probably unlikely in the next few years. We kind of conservatively like to say in a lot of this stuff when we present on it, we would be thrilled in the next few years to get even a low adoption rate of these technologies. So even at that, we're still seeing a significant increase in emissions reductions, and we're just getting it in the community, and that education, that familiarity is what really pays. So, but yeah, I mean, I won't say that it isn't a consideration and it doesn't warrant some additional work ahead of us, but right now we know we've got time, and we know that the grid will look a lot different. We're planning for what we really call smart grid technology in the next several years. So our grid and our load shape of utility use will likely look a lot different 10 or 15 years from now than it does currently. So we're planning for it. Things are changing. What it will look like, I don't know. But
Okay. Have the electric resistance strip efficiencies been updated in recent years? Are they ever replaced and upgraded?
Well, the efficiency of the efficiencies don't really change. They can start to reduce their capacity levels, but again, these are essentially nothing more than toaster ovens, kind of like a big hair dryer, if you will. So for every 1 watt that you purchase, you should get 3.41 BTUs out of them. So, and that's hard electricity. That's hard energy to spend. You know, producing energy with a gas furnace is much less expensive. And keep in mind the heat pumps themselves. If we have a COP of 5, we essentially get 5 times the energy per watt. But what the electric strip heat technology has done is allowed for staging. So we don't have full modulation with them, but we have staging. So for example, if we have a 9 kW electric heat strip, we have a staging potential depending on the air handling system we use, where it may only come on at 3 kW. And if it needs to, it jumps up to 6. And if it needs to, it jumps up to 9. So in general, sized properly, we see much less usage out of them. The older backup heat strips, if you had a 10 kW, it came on at 10 kW. So that's one of the benefits of today's technology is it's smart enough to know that if I don't need all the energy, let's not use it.
Okay. Question regarding 100 amp service and upgrading or not. Some sizable percentage of front range homes have a gas, water, and space heating plus a standard AC unit outdoors. Because the new heat pump will substitute for the AC unit, is it reasonable to expect that the existing AC circuit can be used for the new heating, cooling, hot water heat pump?
It could definitely be used for the outdoor unit component of the heat pump. So remember, we have 2 components. We have an air handling system, a distribution system. So we have an air handling system that moves the air throughout the house. And if you're just changing the outdoor unit, the air conditioner, and upgrading the evaporator coil and even possibly the gas furnace, then you will see minimal changes to your electric need. You may have a 30 amp circuit on that air conditioner now. It may need to be changed to a 40. And as long as the wire that is being run between the panel and the air conditioning unit, you should really see no upgrades. It's just changing a breaker in most cases. The big blow is when you upgrade or change your air handler system from a traditional gas furnace, which is 120 volts, up to an air handling system that's all electric with backup heat strips. And again, you're adding the 208, 240 circuit with, in some cases, up to a 50 or 60 amp maximum overcurrent protection. And then if you add a hot water heater, you could be looking at an additional 30 amps worth of load. So just between those 2 components, we may be looking at additional 90 amps of additional capacity needed of maximum overcurrent protection anyway. So, and that's what we look at. So we had a gentleman who wanted to go 100% electric in his home, but he had a great big home, and his panel was extremely far from the mechanical room, and the panel itself couldn't handle the additional load of what he wanted to do. So instead of scrapping his plans to have a heat pump in his house and being all electric, he decided to go with a dual fuel system where he went with a traditional gas furnace and a heat pump. In his case, that's what made sense. He had a little bit bigger panel than 100 amp, but we've had plenty of people who have 100 amp panels that we have no problems putting heat pumps in.
Great, and I think we addressed this a little bit earlier, but just another question on the comparison cost of a new furnace versus a heat pump.
Yeah, again, furnaces and heat pumps come in all shapes, sizes, and flavors. You can get the Tesla version and all the way down to the Kia Sorento. I don't know. That's a bad comparison, possibly, but the reality is we've got all kinds of different shapes, sizes, flavors out there. If you were going to upgrade, let's let's just say you're going to upgrade to an inverter or cold climate heat pump. And again, every mechanical contracting company out there different. Everybody has a little bit different pricing structure. But if you're going to compare, if you were going to take it and upgrade to and this is not taking into consideration the furnace or the air handling system, but just the heat pump itself, you might expect to spend anywhere between $3,000 and $7,000 more than you would with just a standard 13-SEER single-stage air conditioner. And again, it's hard for me to quantify because there's so many different applications out there. The pricing I'm giving you there would be comparing a moderately efficient air conditioning system versus some of the most efficient heat pumps out there. That would be that $7,000 range.
Okay. If the electrical service to the home needs to be increased, say 100 amp to 200 amp, does the utility pay to provide the added service? And I understand that the electrical panel upgrade would be paid for by the homeowner, but this is the service into the house, I'm assuming.
Currently, it does not. No, if you want to, we run into this from time to time. We run into this occasionally from, and I shouldn't say no, like exclusively. There are scenarios, but typically, if you're looking at an upgrade of service coming into your home from the street or from a vault, you're likely going to pay the increase in cost. Yes, so we're running into this a little bit right now. People are buying homes in Old Town, and then I know in Fort Collins we have one home recently that they were looking at two car charging systems within the garage. So, and I think they were maybe 100 amp service coming. I think that's what they were at in the house. So they were having to go all the way back out and maybe even look at it, even a transformer upgrade where they were at. So currently that is not the case. I think there are discussions on upgrading feeder lines and transformers in the future throughout the city, but that's long term. So right now, if it doesn't exist from the street to your house, that's a cost you would likely bear. Yeah, I've seen numbers as high as $10,000 to come in off the street. So bring a new feeder in and even a transformer upgrade, and then upgrade the service into the house and the panel and everything. So it can get a little spendy.
Okay, I've been waiting since August to get a Carrier Green Speed installed, and now the contractor says it isn't available until May. Are most heat pumps that supply constrained?
Oh my goodness, yes. Very frustrating. I have currently, well, we're going to get an update next week, but we currently have 24 of them we're waiting on. Unfortunately, it's extremely frustrating. The earliest batch that I ordered was, I believe, July. I ordered 5 of them for a large project, and we're waiting on them. Obviously, the supply chain issues we're dealing with is affecting us. One of the biggest hits that we took were the microchips initially. So anything that has technology in it, it was lack of microchips. The reality is this, though: the manufacturers out there, it doesn't matter if it's Carrier, Lennox, Trane, Mitsubishi, all of them have staffing issues within their factories. They're having a hard time producing the equipment. And what they've done initially, or what they did initially, was decide to, in many cases, some of these manufacturers have dropped their product lines. Carrier, for example, had 36 different products that they were producing. They've dropped to 16 so that they could effectively focus on the products that were moving. Heat pumps were not as popular, so why build them? So they were focusing on the bread and butter boxes that were moving quicker. And as much as they don't want to admit that, that's part of the truth. But I think we're starting to see things loosen up. I'm starting to see more Mitsubishi units, but I am waiting. And in general, what I'm being told is, and what I tell consumers is, probably 6 months. If I can get them quicker, great. The reality is they show up at my dock, and I usually don't even know they're coming. And unfortunately, our manufacturers don't know they're coming. Or I'm sorry, our distributors don't know they're coming because the manufacturers are being very tight-lipped of what's on the trucks and what's not. So it is difficult out there right now to get some of the higher-end technology. And what we've been doing is kind of doing a two-step process, primarily in dual fuel applications. If people want a dual fuel system, we go ahead and replace the furnace and the evaporator coil, and we get everything ready to go. So when that heat pump does come in, we can quickly install it, commission it, and get them up and running.
Okay. I'm in Arvada, so outside the Fort Collins programs providers, wanting to get started on a retrofit project. What recommendations for being able to find knowledgeable HVAC contractors, and basically, are there any good heat pump specific contractors in different regions of Colorado?
I don't know if you want to take that, Mike, or yeah, I'll let you go ahead.
I don't, I'm not real familiar with the contractors down there. What I would suggest you do is look at the local utilities companies programs that are out there right now. They do a pretty good job at vetting contractors to ensure the utilities companies, if they're going to support a program, they don't want the run of the mill. They want certified and good contractors to go in there and be able to support their cause. So that would be my suggestion, is see what rebates are available through the city of Arvada or the local utilities companies there. Excel has a great program. There are certified contractors on there, and I definitely look at their list. And Brad, however you want to expand on that, yeah, that would be my suggestion.
That's exactly what I was going to say is a good place to start. And, one of the things that you get with those programs is you get contractors that are under a QA program. So, if they're not meeting the standards required by those programs, they're typically removed from the program. So Mike is right. They are vetted for those programs, and they do agree to a lot of times a little higher standard of installation and craftsmanship and work. So that's a good place to start.
Okay, another comment on mini splits for retrofit. I have a 2 compressor system, 30,000 each, with 6 total heads that have worked well for 2 years, with the old ducted gas system supplementing only once when temperatures drop to -9. So don't write off the efficient mini splits for retrofit. So just a comment. 30 years ago, Florida Power and Light paid my parents to add an AC refrigerant condenser to water heat exchanger to their water heater to save electricity by using the AC to heat the water. I haven't seen this here. Is that something that's done anymore?
Well, I haven't seen it with air conditioning. There's a hate to say phenomena. It's not. It's a part of the refrigeration circuit is what's called de-superheating. So anytime that we change the refrigerant back from a gas to a liquid, we have to de-superheat it first. And when that happens, we get a byproduct. We get energy. So ground source heat pumps come with a little cool little component on them called the de-superheater. So it doesn't matter if the system's running on heat or cool. It can grab the energy from the de-superheating process, run it through a pump system that's attached to the water heater, and essentially give you not free hot water, but some hot water. So in a lot of cases, what it does is you're able to supplement some of your hot water. So I'm not sure if that's what they were referring to or if that's what they were going for, but it sounds like that would be one of the only things I can think of off the top of my head, how they would use that energy coming from the de-superheating process of an air conditioning system to, in fact, heat hot water. But it's very common with a geothermal unit. They actually come with that component built in.
Okay, sorry. What is the payback range in years on replacing an existing gas furnace with heat pump, electric assist forced air from older, lower efficiency units to a newer 90% plus efficiency unit?
Great question. That's one we try and calculate for people so they can see what their return on investment is based on their specific choices. I've seen them as low as 6 years. I've seen them as high as 45 years or even 50 years. Now, of course, the equipment's not going to last that long. Where you're going to see your best return on investment in a situation like that, you got to consider right now. If you're looking at it from a return on financial investment, comparing what the heat pump can do in extreme conditions versus what a high efficiency 98% modulating gas furnace can do, it's not a fair comparison. Natural gas is still very, very inexpensive. So that's where we start to see the return on investment start to slide down the other direction. Okay, but if you're considering having a solar component put on your home as well, that's where you see the return on investment slide much more towards the heat pump. I've seen as low as 3 years when we can start to produce that energy. So to give an average of what we're seeing, if we're going to take a high efficiency inverter heat pump with even backup electric heat strips that's sized properly and has a good balance point versus a standard 80% efficient furnace with a 8 or 10 SEER air conditioner, you're probably going to see somewhere in the neighborhood of 6 to 7 years on average. And that's me with just the data in my head with nothing to back it up, just based on some of the assessments we've done and the audits we've done.
Okay, we are at our time limit, and I apologize, folks, because there are a lot of additional questions we will probably never get through because it will keep on growing. Well, I just want to, first of all, thank Brad and Mike for joining us. This is an area I think we'll probably continue to revisit in the coming years as things improve. But we could even get even more strange and start talking about, split hot water systems, which I've been geeking out on a little bit recently. And then, of course, solar thermal, which we used to do a lot of. I could see 2 or 3 old solar flat plate systems out my back window. They're all gone now. People got new roofs, but one person put on PV, so I got a little switch off there. But hey, I want to thank you all again, and for everyone who attended, you should get a link to the recording in a follow-up email that automatically goes out tomorrow. If for some reason you don't, just send me a note at either the info@crest-energy.org or p.eberle, E-B-E-R-L-E, @crest-energy.org. So again, thanks a lot, and everyone have a great evening.
Thanks for the opportunity.
Thanks so much.